All right, folks, for lesson 2, we are going to talk about rational functions. We're going to build on how we graphed the reciprocal function y equals 1 over x, and we're going to expand on that to understand a little more about asymptotes, explore intercepts, and explore other holes and characteristics of these graphs of these functions. We're actually going to have you do some graphing at the end, and then we will discuss it in class, but I do want you to give these kind of a fair shot just to kind of see what these will be like. There's a lot of information here. And so organizing your notes is going to be really critical to success. If you're going to want to be able to graph these rational functions, have a prediction and an understanding of what those will look like before you use your grapher, you're going to set yourself up for success. But that does require you to be neat and organized with a couple key ideas, just to make sure that you can reference your information while you are doing your classwork. All right, so first of all, we want to talk about what rational functions are. Basically, a function that can be expressed as the ratio of two polynomials is considered a rational function. You have to have a variable in your denominator where the value of that denominator can't equal 0, right? We know that we can't divide by 0, but we have a polynomial on top, a polynomial on bottom, and it's a ratio of polynomials. That's what makes it a rational function. And here are some examples of what some of those graphs will look like. You can see that there are some asymptotes, horizontal and vertical, etc. We're going to explore some of these pictures and see what these graphs will look like as we learn a little bit of the nuances of these functions. We already explored a little bit about horizontal and vertical asymptotes, but when we are talking about rational functions as a whole, not just the reciprocal function, but all rational functions, the graph will have at most one horizontal asymptote. There will only be one ever if there ever is one. Now the graph might cross that horizontal asymptote, but what we want to see is what happens as the graph moves on towards positive infinity or negative infinity. We're really considering that end behavior, and we're kind of considering how the graph maybe approaches that value, even if it bounces above and below that horizontal asymptote. All right, but obviously we're looking at the extreme left and extreme right, and along the way we'll see how it happens as we get there. By extreme left, I mean negative infinity, positive infinity, okay? And so we want to make sure that we can find the horizontal asymptote, but in order to do that, we have to be in standard form, meaning it can't be factored. We'd have to unfactor it, right? Do that multiplication that we've been practicing. We will get to do some factoring, so we're not off the hook for that. But here are 3 different cases that we want to explore to make sure that we can identify what the horizontal asymptote will be without actually graphing the rational function. So if the degree of the numerator is less than the degree of the denominator, then that means we have something where we have basically a 1 over x recipe. Like if this were to simplify and you canceled out the common factor of an x squared over x squared, we'd be left with a 1 over x. And so we know that there will be a horizontal asymptote. That's not what we're doing, but that kind of helps us predict that if the degree of the numerator is less than the degree of the denominator, the horizontal asymptote will be y equals 0, that horizontal line y equals 0. Case number 2, if they have the same degree, these are both quadratics, maybe they're both linears, maybe both cubics, if they're the same degree in numerator and denominator, then the horizontal asymptote will be y equals the ratio of that lead coefficient. So in this case, 6 over 2 would give us 3. So y equals 3 is where that horizontal asymptote is. All right, so keep these 3 cases organized, maybe color code. You'll notice I had an orange box, a blue box, and then I'll have a green box. For case number 3, if the degree of the numerator is bigger than the degree of the denominator, then there is no horizontal asymptote. There may be other asymptotes, there may be other aspects of this graph that we can explore and understand, but there will be no horizontal asymptotes if the degree of the numerator is greater than the degree of the denominator. Keeping that straight is challenging, all right? So make sure that you're setting yourself up for success, all right? Organize your notes, have those readily available and accessible while you do your work. And while we do this work, so you'll be able to reference those. I'd have to click back through if I don't remember these. And so let's try to understand exactly what we are dealing with in this situation. Here, these have the same degree. These are both degree 1. So this is case number 2, all right, where they have the same degree. So that means that my horizontal asymptote is going to be at y equals the lead coefficients there, 2/3, all right? They have the same degree. And so I know that my horizontal asymptote will be 2/3. I don't have to put that in my grapher to know that. Over here, this is not in standard form, But I can predict that this is going to be an x squared, right? And so I know that the degree on top is going to be bigger. Degree on top, the numerator degree is greater than the denominator degree. All right? Which means if my numerator degree is bigger than my denominator degree, that there is no horizontal asymptote. Now I did say it has to be in standard form. We could write that in standard form just to make sure we get x squared minus 4 over 3x minus 6. But we can predict already if those are multiplied, we know that we're going to get an x squared, and that's bigger than x to the first. So there is no horizontal asymptote on example B. All right, pause the video if I'm going too quickly. Replay some of that if we need better explanation. But that is case number 3. I should write that here. Case number 3. Case number 3. And so make sure that you have that so that you can reference case 1, case 2, case 3. And then that will help you determine how you're going to make this judgment call to know what the horizontal asymptote will be. I want for you to try letter C, and then I will do letter D. All right, so you will try that one. Pause the video if you need to. I'm going to go into letter D here. This, we're going to have an x squared and an x squared. So I know that these are going to be the same degree, numerator and denominator, which means that this is case number 2, right? It's going to be case number 2 where they are the same degree, which means that the numerator's ratio is going to be, not the numerator, the lead coefficients ratio is going to be the horizontal asymptote. So I do have to multiply this out. Now, a little trick and strategy, we know that we're going to have a 2x and a 2x, so we're going to get 4x squared. I know that I'm going to have an x and an x, so I'm going to have a 1x squared. So I know that y is equal to 4 as the coefficient over 1 as the coefficient is going to be the horizontal asymptote. All right? Now I should multiply those out just to do a good, be a good model here, role model of how we do that. So we're going to get 4x squared minus 9. This is going to be x squared plus 2x minus 15, multiplying those out. And so hopefully we can see now that there's a 4 over 1, so the horizontal asymptote is y equals 4. All right? If there's any part of that messed with you, write a little asterisk, write a little question there for your teacher. All right, vertical asymptotes and holes. I mentioned holes at the beginning, and it was like, surprise, there's going to be holes in the graph, and you're like, what does that even mean? And so we will chat through that, obviously. But a vertical asymptote only happens when the denominator is equal to 0, right? Because we're not allowed to divide by 0. So that just makes things get a little messy as we get close to the value of x that would make our denominator equal to 0. All right? So that's vertical asymptotes. We're familiar with that already. We dealt with that last time. But here, we're going to learn about a hole. All right? Now, you can have a hole in the graph where there is no output for that value of x, and it's just a little bit disconnected from the graph. It's basically a non-continuous path here where you have to pick up the pencil and trace again. You don't see those in your grapher. This you can see in your grapher, not the dashed line, but you can tell, oh, they're not having the same output. They're not given an output here. But here we can't see that in the grapher, so we have to know that it's there. And how can we know that it's there? You might be able to see it in your table, but if it's a fractional value, that's not helpful. And so that requires us to be in factored form. The hole happens where you have a common 0 in the polynomial of the numerator and the polynomial of the denominator. So here, let me show you what this means. If this is in factored form, I get x minus 4 over x minus, 4 times x plus 2, all right? So here, I've got this common factor in the numerator, right? Where x equals 4 makes the numerator 0 and it makes the denominator 0. So if this were to simplify, it would be 1 over x plus 2, which is this picture, right? The reciprocal function moved left 2 spaces, but we have to address that there was something there in the original function that is causing some problems, right? So we're going to address that when we draw the graph. We're going to draw basically a circle there on the graph, all right? You won't see this in your grapher, but it's there, and we have to articulate that. All right, so again, finding the vertical asymptotes, that's where the denominator equals 0 for that x value, but only the denominator, right? Over here, if it's both numerator and denominator have 0 at that x value, then we're going to have a hole. All right, so this is why we have to do factored form. I said we weren't going to get away with that. So I'm going to do a couple of these, and I'm going to have you do a couple. And lucky for us, these are already factored. Hooray! All right, so I see that there's a common factor in numerator and denominator. So that means that there will be a hole at x equals positive 2, right? And when x minus 2 equals 0, so x equals 2 is where there's a hole. There will be a vertical asymptote at the vertical line, x equals, when does this equal 0? When x equals add 3 divided by 4, 3/4. Okay? Again, if you're having trouble with the math on this, I get x equals 2 by taking x minus 2 equals 0 and adding 2 on both sides. I get x equals 3/4, just like last unit, by setting this factor equal to 0. I add 3, I divide by 4. Sorry if you can't see that marker very well, it's kind of dying. I'm doing my best. All right, over here, we can see that we have a denominator where we can't have x equal 2. X is not allowed to equal 2, but since that's in numerator and denominator, we know that that's going to be a whole at x equals positive 2. Now here's what's weird about this one. The way that this looks is we have a quadratic divided by a linear, and we know what the graph y equals 4x minus 3 looks like, right? That's going to be, this really steep graph like this. But when x is equal to 2, there's going to be a hole in the graph. It's going to look like a line when we type it in our grapher. If we were to type that in our graph calculator, it would be like, that just looks like a line. But upon closer inspection, you would see, ooh, there's kind of a gap here. There's an error in the outputs for x equals positive 2, right? It's not an actual output value. All right, I will do this one, and I'm going to have you try letter D. And again, these are just try. Give them a shot. Like, what's the worst going to happen? The worst that can happen is what? You don't get it right? That's actually not the worst. The worst is that you don't do it, and then you lose points on your work. Womp, womp, womp. All right, so here we're going to have to factor these bad boys. And so when we are factoring these, I want to do a good job of factoring this. This is going to be, I know it's going to be a 2x and an x. I need to get negative 42 here, so it's going to see negative, what do I need, 6 and 7. If I do 6, that's not going to work. So I need to have 84 factors, 8 and 12. I'm kind of slow, give me a minute. So this is going to be 6, and this is going to be, this is going to be negative 4 and 6. Nope, that's not right either. That's not giving us 42. I need to get 7, and we'll see. It's got to be 14 and 3 is going to get us to 42. But that's okay. That's what we want. We want 14. So this is negative 14, and this is 3. So let's double check that. This is going to give us 2x squared. This is going to give us negative, that's negative 28. That's not quite right. I keep messing up my factoring. I should know algebra 2. We got a common factor. Come on, bro. All right, so common factor. Here we go. X squared minus 4x minus 21. Okay, this will be way easier to factor. So now I've got x minus 7 and x plus 3. I need a new marker. Trash. All right, and then in my denominator, I've got 2x and an x. I've got a positive 3 to make 6 x's and another positive 3 to make 9 x's. Okay, so sorry for the flub there. All right, so here we're going to see that there's a hole at x equals negative 3. All right, there's a hole at x equals negative 3. But there's another 0 here in the denominator, and so there's a vertical asymptote at x equals negative 3/2. All right, you see how fast it is once it's factored? It's great. If you're messing with the factoring, you're like, what do I do? This one will be really easy for you to factor. So go ahead and handle that one. Find the holes if there are any. Find the vertical asymptotes if there are any. And we'll go from there. The next part, I told you there's a ton of information. So we dealt with horizontal asymptotes. We dealt with vertical asymptotes. Now we're going to deal with intercepts. All right, and all of these are aspects of the graph. All right, of the graphs of our rational functions. So you know what y-intercepts are. That's the point on the graph where x is equal to 0, right? Because x equals 0 is the vertical line, and it's where does the graph cross the y-axis, right? Where in x equals 0, what is the y value? So if you're going to find the y-intercept, just plug x equals 0, see what happens, right? That's not too challenging. The hard part is always finding the x-intercept. That's generally what we're dealing with. And what we wrestled with in the last unit was finding the zeros of our polynomial functions, right? Those were the x-intercepts for those polynomial functions. And so this is where the y value is equal to 0. So we're going to set y equal to 0, or set the function equal to 0. Really, the only time that happens is when the numerator equals 0, right? But we have to be aware if there are holes, etc. And so we want to look at the numerator. We want to make sure that we can make it so that the numerator does not equal 0. Or, I'm sorry, so the numerator does equal 0. When the numerator equals 0, that means that our fraction is equal to 0, right? That's why when we did our reciprocal function, y equals 1 over x, it would never have an output equal to 0, right? Because the numerator was always going to be 1. So the question here is, when we're finding x-intercepts, can we find a place where the numerator equals 0, all right? So let's go ahead and I'll do a couple of these and I'll have you do a couple as well. So on these, I want to make sure that we do a good job, maybe a better job factoring than I did in the last one. And so this will factor as y equals 3, actually, but let's start with the y-intercept. So the y-intercept happens when x equals 0. So if x equals 0, boop, 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 we are left with y equals negative 8 over 2, y is equal to negative 4. So the point 0 comma negative 4 is the y-intercept. That's pretty straightforward. Over here, same deal. If x equals 0, that's 0, that's 0, that's 0, that's 0. So the y-intercept happens when x equals 0. That means here we have 0 over negative 12, which is 0. All right, so that means that the point 0 comma 0 is the y-intercept. We plug in x equals 0 and we see what y value we get out. All right, it's important to note that 0 and 0 adds up to 0. All right, and then 0 plus 0 minus 12 is going to give us negative 12. So those are the y-intercepts. Those are pretty straightforward. The x-intercepts, right, those are the hard ones. So when does this thing equal 0? All right, when does this polynomial equal 0? Well, it happens when the numerator equals 0, all right? But we can divide out any holes, right? We can divide those out. So we want to do a good job factoring. Let's see here. 3, x, and my denominator, I'm going to have 2x and x. And so I've got to do a good job here. We've got 2x, let's see, positive. Let's see, I need a negative 2 and a negative 1. That's going to give me negative 4x and negative 1x. It makes my negative 5, and these multiply to give me positive 2. Over here, I need factors. I need these to multiply to equal negative 8, and then the product to add here. So negative 24. We're going to do minus 8 and plus 1. That's negative 8x and positive 3x. Okay, good. So here, when does this equal 0? Well, there are no holes in here. So really all that I'm going to care about is when does 3x minus 8 times x plus 1 equal 0? And so this will tell us both of our zeros. X will equal 8/3, x will equal negative 1, meaning 8/3 comma 0 and negative 1 comma 0 are our x-intercepts. On this one, we want to be able to factor numerator and denominator. And so in the denominator there, we're going to have, let's see what we've got here. We've got, if I factor out a negative 2x, that gives me x squared minus 9. Okay, so that'll factor as x plus 3x minus 3. Doing our quadratic factoring. And then for this one, we got 2x and x. Looks like we're going to have an x plus 3. Ooh, this will be a plus 3, and that'll be a, this will be a minus 3, and that'll be a plus 4. Minus 3 plus 4. Let's double check that. 8 minus 3 is going to give me 5. There's my negative 12. There's my 2x. Okay, good. All right, so here we want to check to see, are there any common pieces in the numerator and denominator? There are no holes here, so we're in very good shape. But we want to consider ourselves, or concern ourselves with the numerator. All right, so again, we had to factor it. Now we want to look at this numerator. I'm going to write up here, I've already done the y-intercept. So when does negative 2x and x plus 3 and x minus 3 equal 0? Well, that happens when x equals 0, when x equals negative 3, and when x equals positive 3. So that means that 0 comma 0, negative 3 comma 0, and positive 3 comma 0 are the x-intercepts. Now I know that's, sorry for the bell, I know that that's a little challenging for us to do, but again, all that work that we did last unit where we were finding those zeros is going to be a huge part of our efforts today. All right, now I did a lot of work there, and that was a long set of notes. You've got the weekend to take care of this. On this part, here's what I want for you to do. You are going to come to class with, and these are going to be included in your notes, these items. Now you're going to try to sketch them If the sketch fails, I'm fine with that. We're gonna talk about that in class. So I'm not super concerned with trying the sketch. Try your best. But what I want for you to do on these items is I want for us to get ourselves ready to graph these, all right? Without our grapher, all right? I know that's a little challenging, but what if you found all the asymptotes, all the holes, all the intercepts? Find all of those things, and then see if you can piece together what the sketch will look like. We did some graphing of our rational functions, and so or of our reciprocal functions, so I want to see how that looks for you if you give these a shot and take a look at what these might be like. We will do these in class, but you need to have this part done. Find the asymptotes, find the holes, find the intercepts, just like we did in those prior examples. Whew! I told you there's a ton of stuff here, but it's going to be glorious.